To predict how high a river will rise, civil engineers have to solve a single massive accounting problem, calculating exactly how much rainwater will stay on the surface and how much will disappear into the ground. Hydrology rests on this mass balance equation: precipitation minus losses equals final surface runoff. Of all pathways pulling water out, evaporation, canopy interception, or depressions, the volume of water absorbed directly by soil dictates the final runoff. Horton's infiltration curve maps the physical reality of soil absorption. Earth doesn't take in water at a steady pace. Soil begins with a high initial capacity, F0. As the ground saturates, absorption exponentially decays to a final steady constant, Fc. While it is possible to model this curve mathematically, applying it across a vast, varied river basin is difficult. We rarely have the precise soil data required to define these exponential decay constants for every acre of a large catchment. To bypass these data gaps and maintain practical forecasting, civil engineers abstract the complex physics of soil absorption into blunt, flat averages. This chart is a hyetograph. It plots the intensity of a storm against time, and it is the primary tool engineers use to map out these abstractions. Instead of a continuous flow, storm duration is divided into discrete time intervals, represented by vertical bars. To simplify the math, engineers apply an infiltration index. When rain hits the ground, it doesn't all become runoff. Some of it evaporates back into the air or gets trapped in depressions, and a significant portion infiltrates downward into the soil. For the AEE civil exams, a recurring challenge is calculating the precise average rate of that downward infiltration. We measure this rate using two distinct metrics. The W index averages the infiltration rate across the entire duration of the storm. The phi index, however, takes a much narrower view. It calculates an effective rate by looking only at the specific periods that actually produce runoff. Look at the math side by side. The W index divides the total infiltration by T, the total time of the storm. The phi index divides by TE, the effective time, meaning only the hours where rainfall intensity exceeded the infiltration capacity. Mixing up the total duration of the storm with that effective runoff-producing duration is the most common reason aspirants lose points on these problems. Calculating the W index is straight arithmetic. If a 4-hour storm drops 9.8 centimeters of rain, produces 3.6 centimeters of runoff, and surface retention is 0, you subtract the runoff from the total rain to get your total infiltration. Divide that remaining 6.2 centimeters by the full 4 hours, and you get a W index of 1.55 centimeters per hour. The phi index introduces a logical trap. If the storm starts with a light drizzle that entirely soaks into the ground, that hour produces 0 runoff. For the phi index calculation, that hour cannot be counted in the time denominator. This chart illustrates exactly how we prune that ineffective rainfall. The horizontal line represents the phi index. Any part of the bar graph below that line is absorbed by the ground. Only the hatched areas rising above the line represent effective rainfall that contributes to runoff. If a bar doesn't cross the line, that time period is discarded. Because you don't know the final phi index line until you calculate it, but you need to know which hours to discard to make that calculation, you have to use a trial and error method to find the answer. This data table breaks down the hourly rainfall for a classic 9-hour storm. We have 16.7 centimeters of total rainfall and 9.3 centimeters of runoff. Subtracting those gives us a total infiltration of 7.4 centimeters. For the first trial, assume every single hour produced runoff. Divide the 7.4 centimeters of infiltration by the full 9 hours. That gives an initial, temporary phi index of 0.822 centimeters per hour. Now look closely at the hourly data. Pause the video and identify which specific hours recorded less than 0.822 centimeters of rainfall. The values for hour 1, hour 8, and hour 9 are all below 0.822. Those periods did not produce runoff, so they are entirely ineffective and must be removed. Now we adjust both the infiltration and the time for trial 2. Subtract the rainfall from those 3 discarded hours from the 7.4 total. Since we threw out 3 hours, divide the new number by the remaining 6 effective hours. This resolves to 0.9 centimeters per hour, the final correct phi index. This iterative mathematical pruning is the only reliable way to isolate the periods of true rainfall excess. By definition, the W index includes all initial losses and spreads the average over the maximum possible time. The phi index removes those low-intensity periods, shrinking the denominator and raising the rate. Because of this, the W index will always be mathematically lower than the phi index. Memorize this inequality to quickly eliminate impossible answer choices on multiple-choice questions. Keep their distinct applications in mind. Use the W index for large, heterogeneous basins, where a broad average is sufficient. Rely on the phi index when the problem requires precise flood forecasting. During the exam, constantly check your units. Do not mistake a total volume of infiltration measured in centimeters for an intensity rate measured in centimeters per hour. By distinguishing between total duration and effective duration and methodically applying the trial algorithm, you will navigate these hydrology questions with complete accuracy.